something I forgot about the proof here. So you eventually get a diagonal matrix. But how do you get to powers of pi? So you eventually, after some time, you get to a diagonal matrix. You get to x1 times xd. And every xd, this is actually an important fact. In fact, it could be written as pi to the ni times yi with yi a unit of area. So literally, we just take yi to be pi to the minus n. I'm sorry, pi to the minus valuation of xi times xi. The valuation of this is 0, right? 0. This has 0 valuation, and thus it lies in rho star. And well, you take ni to be minus v of xi. I'm sorry, you take ni to be v of xi. So you could always end up having powers of pi. Okay. So one more thing about lattices. We have actions of GLD and PGLD. So recall that GLDF is just the invariable matrices. Matrices over F. GLD O, same thing but with O. PGLD, oh, okay, before that. So how GLD F acts transitively on lattices. And how does it act? So if I have a lattice L, so G times L is, well, GL, G of L. Just the image of G on L. That's also a lattice. So if L happens to be sigma over I, O vi, then this is also equal to sigma of I, O G vi. This is the action. So it acts on lattices. And why is the action transitive? Because, well, I could just write, I don't know, I could just write the basis in, say, matrix form. I could just write, I could think of these as column vectors, right? And there is this is going to form an invertible matrix in GLN. So I should say, well, and I could always move between two bases of F by an element of GLNF. Okay, well, just write this GLNF acts transitively since it acts transitively on bases FDD. So what is an invertible matrix? It's just an invertible matrix. It even acts simply transitively. Just in case someone doesn't know, transitive means that there is only one orbit to the action. So I could move between every two elements via the action. definition. So two lattices L and L prime lattices E to the D are equivalent, denoted L equivalent to L prime, if there exists some element of F such that F is X times F prime. This is an equivalence relation. I denote by square brackets L the equivalence class of L. And notice that, well, GLN of F acts on the equivalence classes.
That's right. X, L equals X. Right?
Sorry? Huh?
Second line at the end.
Oh, sorry. Yes. L equals X times L prime. Yes. So this is L. Lattice. However, well, now you know that inside this group I have F star embedding diagonally inside the general linear group.
I think you also want to take the X and the S.
I'm sorry?
The X and S.
Oh, yes. Okay. Yes. So we have F star inside GL and F. And that means that PGLN F, which is just GLN F over F star, it acts on equivalence classes of lattices. This is going to be lattice. So yeah, I could actually define an action of the quotient group, because this part acts trivially on the equivalence classes. This is well defined. For example, and notice that the stabilizer in GLNF of O to the N, what would be the stabilizer? So I have a basis, so I have this lattice, so the stabilizer is just going to be GLN O, namely matrices which are invertible over O. So this would fix O to the D. This GLD. Where else did I put that?
Everywhere.
Really? How frustrating. Okay, I hope we got all of them. And the stabilizer of inside PGLD F of the equivalence class of O to the D is no wonder PGLD of O, which is just GL D O over O star, which naturally embeds in PGLDF in the obvious way. And the action of PGLD is transitive. It acts transitively. This is going to be important. Okay, we're finally ready to define the building. So, the definition and construction. Of building. Wait a second. Well, before it, sorry, almost. So the conclusion of this thing with the stabilizer, some conclusion. So speaking about lattices is the same as speaking about GLNF over GLNO. This is the same object, namely, just give me just give me the coset, and I will send it to G times O to the N, O to the D. Why do I keep writing N? Okay, this is the equivalence. So just write your lattice as something as G times O to the D, and send it to the coset. And equivalence classes of lattices. Equivalence of lattices is the same thing as PGLD F over PGLD O. Again, so the coset PGLD G times PGLDO corresponds to the equivalence class of G times O to the D. So that this is clear because of this stabilizer thing. So it is sometimes useful to view lattices as matrices and vice versa. So if I have, by the way, if I have a lattice here, if you want something more explicit, GDO. So this is just going to go. This is one direction, and this is the other direction. Just think of these as column matrices. So this is V1, VD times GLD. Oh, hope I'm not mistaken here. Hopefully not. So you just pick your favorite basis and take the matrix. That's the correspondence. And then the other way around, you take the matrix and apply it to the standard basis. And the same here. Okay. So the affine building GLD. So I'm going to construct a simplicial complex. I'm calling it a building because it comes with some additional structure. There is some combinatorial properties to it, but we are not going to focus on them today. So it's going to be a simplicial complex. So we construct an infinite simplicial complex X as follows. So the vertices of X are going to be equivalence classes of lattices. Inside F to the D. So here's the reason why I spoke half the lesson, half this lecture about them. So what about edges? So L is adjacent to L prime if exists some X such that L X times L prime lies somewhere between L and pi L. This is the adjacency relation. Notice that this relation is symmetric. Since this implies that xl prime contains pi L, contains pi x L prime, and of course I could divide by x to the minus 1 and get this. So this relation is symmetric, and it is independent of the class, the representative chosen in the class. So these would form the edges of the complex. What about higher cells? So, high-dimensional cells are just sets of cells element L1 to Li, such that all of them has to be distinct, such that LA is adjacent to LB for all AB. So, I mean, the thing is this. If I see a triangle, then I feel it. If I see a pyramid, then I feel it. That's how it works. This is also called the clique complex, because my simplices are just my I simplices are just the I cliques in the underlying graph of X. Okay? Questions about it?
In order to have I cell, you need I plus 1.
Oh, sorry. Correct you are. Yes. Okay. So claim X is d-dimensional. Sorry, d minus 1 dimensional. More precisely, so 1, every cell is contained in a d minus 1 cell. Of course, not unique. And there are no d cells. Or if you want, x d z. So let us fix some cell L1 to LD. Now I'm going to, to Li plus 1 some ice. This is to prove 1. Now I'm going to apply a principle which would repeat itself several times. So we have an action of PGLD, F, right? And the action is transitive, and moreover, notice that the action of PGLD respects the adjacency we just defined on the vertices. So if L and L prime are adjacent, then so is, and if I multiply both by some element G, then they're still adjacent. So without loss of generality, L1 is just O to the D. Why not? Maybe Li plus 1. More comfortable. Okay, because I could just multiply by some element. So otherwise, multiply by suitable element of PGL DF. And this action respects the adjacency. I would still get a cell. I would still get a click. Okay. So now, what do I have? So I have L1 to LD are all adjacent to O to the D, which means that, so I have here pi of O to the D, and somewhere in between I have L1 to LD, I'm sorry, not to L, to Li, sorry, to Li, and here is O to the D. Well, right? I could replace the LIs by some x times Li if needed. Since, well, moreover, since Li is adjacent to Lj, well, I'm using the notation here, so Li is adjacent to Lb. When I choose these representatives here, either LA is contained in LB or LB is contained in LA. And why is this true? Okay, this means that LB is contained in, I know, XLA contained in pi LB. Or, well, I could choose LA. Let's see. Okay, this is true for some x. Why is it true for x equals 1? The reason is that everything lies here. So how do I do that? Well, it should be very simple. So the thing is that this is O to the D, and I know that LA lies here. Anyway, this should be obvious.
I think it's because you can choose bases for all of them such that there will exist a set of integers for each k such that it...
Okay, yeah, I see. Oh, okay. Yes, okay, you're right. So, proof. Oh, this is like a subclaim. So, subclaim. L is less than or equal to A. So, let's continue this.
Thanks.
this here. So, so we can, I don't know, we could choose, I don't know, basis. No, it doesn't work so well. Let's just. Okay, I'm sorry about this point. I need to check it. But the thing is that since all of them are here, they are bounded in between, they form a full flag. Okay, I need to check this. The proof is not so hard anyway. But I owe you this. And this means that without loss of generality, I have pi O to the d, and here is L1, L2. These are all different, of course. Here is Li, and here is O to the d. So now I could just divide. So mod by pi O to the d. Now, what is O to the d over pi O to the d? So if you're, this is just O over pi O to the d, which is just our residue field to the d. So it's a d-dimensional vector space. So this sequence is nothing but a chain of vector spaces. This is what going to be 0, contained in, I don't know, V1, contained in Vi, contained in K. And these are all K vector spaces. Well, but this is d-dimensional. So the longest chain I could have is of length d to the minus 1. So this immediately implies that I is less than or equal to d minus 1. This actually proves part 2 of the claim here. So there are no d cells. It cannot happen. Otherwise, I would get a chain of length d inside a d-dimensional space. And moreover, this proves that, I don't know, the chain Vi, say Vn, n equals 1 to I, can be refined. Refined to a chain of length d minus 1, which in turn, so I could just lift the chain to a chain of lattices, gives rise to a chain of lattices of d minus 1 lattices, i.e. a d minus 1 cell containing our I cell. So this completes the proof. This proves 1. So every cell is contained in some d cell, and there are no, I'm sorry, every cell is contained in a d minus 1 cell, and there are no d cells. So apart from this point, which is technical, and I don't want to fumble around it, so this is proven. So there are some, let's say, deeper combinatorial properties. So I'm not going, I plan to prove it for the case d equals 2. I hope we would have have time, but I will state it anyway. So X is connected and contractible. When I say contractible, I mean if you realize it as a metric, as a topological space by just gluing the relevant simplices instead of the abstract simplices, then you get a contractible topological space. So this is a fact. I think we would prove it for d equals 2. But before that, well, what I want to, in fact, this is what I hoped to achieve today, but I probably won't make it. If d equals 2 and the size of k is q, then x, which is just a one-dimensional complex, it's a graph, is the q plus 1 regular tree. So, I don't know, it looks like this. That is x. I don't know, here is going to be O squared, and all the lattices. And this is going to be the equivalence class of O squared, and everything is going to split from it. So I hope we could show this today. Anyway, what I want you to think is that the building is kind of generalization of the tree. Because the tree, well, what is the tree? So we take a lot of lines. So I know we take a lot of lines. This is a line. And we glue them together, and we get the tree. So here I have lots of lines, right? These are the so-called apartments of the building. This is part of the additional combinatorial structure that I have omitted. And in the case of d greater than 2, for example, in the case of d equals 3, so sorry?
Apartments?
So the lines, just all the lines inside the tree. The tree is just, these are the apartments. Forget I said that. So in the case of d equals 3, so everything is going to look like this. So we would have a lot of planes tiled with triangles glued together in some fashion, so that anyway, we have triangle, we have lots of triangles here. So it's going to be some kind of generalization of the tree, some natural generalization. So it's going to be a lot of these glued together. This is what's going to happen. I don't know, here it would continue, etc. And it explodes like the tree does. Okay, so I want to speak about some combinatorial properties of X. So, coloring. So X has a natural coloring. There is a color function. So C from X to Z over D. This is the color function. And here it's going to be, I don't know, it would be more beneficial to define it using the matrix representation. So now I have a coset of PGL DO. So what will be the color of this? So the color is going to be the evaluation of the determinant of G mod D. This is going to be the color. So why is this well defined? So notice that the determinant of a matrix here, well, the determinant of a matrix in GLD lives in O star. So the valuation does not affect so much, but however, PGLD, I have modded out by some, I mean, if I mod out by F star, if I mod out by a diagonal matrix and something of the form x, 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 so the determinant is x to the n, x to the d, and the valuation is vx times d, but this cancels out since I make mod d. So it's well defined nevertheless. And if you want a definition in terms of lattices, so the color of L is log log Q, where Q is the size of the residue field. Let's suppose it's finite. Log K such of O to the D over L. So I could always choose L. This is mod D. I could always choose L, which is contained in O to the D. Right? I could just multiply it by some large number in F, and it would be eventually contained in O to the D. So, and then I have an index, which is Q to the something. Take log and make mod D, and this is what happens. So what happens if I take, I don't know, instead of L, if I take XL, or if I take pi L, so notice that L over pi L is Q to the D. So this would cancel out. It doesn't matter. So it's well defined. Is that okay? And for example, I don't know, the color of O to the D is 0. The color of, I don't know, O E1, O pi E1 plus O E2 plus etc. plus O E D is just 1, because I have index Q inside here, and I take the log. So notice that the action of G of PGLDF does not preserve colors. However, the action of SLDF does preserve colors. And the reason is that here I have matrices of determinant 1, and this is determined by the determinant, so it does not affect anything.
It's transitive,
So this is not transitive, but this is transitive on the vertices of
PGL, you said that X transitively, so.
yeah.
Maybe,
Okay, yeah. So this is the part. So if large C is a cell, then the color of C is just defined to be the set of colors in C. So this is C, C, L, for every L in C. Notice that the size of this group is always the dimension of L plus 1. Because, why is this? So it's written here. So let's go back to this picture. So if I have a cell, so these lattices have to be of different indices inside O to the D. These lattices have to be of different indices, so they have these different colors. Okay?
The dimension of, right?
The dimension of the cell, namely just the size of the cell. This is just the size of the cell.
So you wrote lattice.
Hmm?
You wrote dimension
Oh.
of lattice.
Sorry. Yes. Sorry. Anyway, this follows from the fact that if you have a click, then between several vertices, that they cannot be of the same color exactly because of this sequence. Also, if xy is a directed edge, meaning that, well, x and y are adjacent, and I just put x in front of y, then the color of xy is just the color of y minus the color of x. This is also a this is also a useful definition, and the reason is so notice PGLDF preserves the color of directed edges. So it does not preserve the color of the vertices, but it does preserve the color of the directed edges. So here's a proof. So right, I don't know, x is L and y is L prime. So without loss of generality, L is contained in L prime, contained in O to the D. So the color, let's say Q to the color of xy, this is Q to the color of L prime minus Q to the color of L. But this is just, well, this is Q to the color of L prime over Q to the color of L, which is just O to the D over L prime, O to the D over L, which is just L prime over L. But for all G in GLDF or VGLD doesn't matter. GL prime over GL is the same as L over L prime. So the action of PGLD on these does not change the color of the directed edge. Is this clear? I did it somewhat quickly since we're almost out of time. Actually, I want to keep this. So I will finish with the following claim. So proposition X is regular in the following sense. if I containing J containing Z over D is a set of colors, and C inside X is a cell of color I, then the number of C prime of color. So color of C prime is J, and C prime contains C is independent of C. It only depends on I and J. So if it was a tree, for instance, then this would mean that the tree is regular. Because, so if I have a vertex, I'm saying that the number of edges emanating from the vertex is independent of the vertex. It only depends on the color that I choose. So as a colored simplicial complex, it's regular. Everything looks the same.
Is this the same as what Alex explained? Yes. This is the same.
Almost. So the way to show this is to claim the following. So the way to show this is to show that show the following theorem, which is PGL-DF acts transitively, actually PSL. Namely, those matrices of determinant 1 modulo the center, the elements in F star. Acts transitively on B-1 cells. And this is essentially the proof. So what you do, you sort of you embed C inside a D-1 dimensional cell. And let's say you have another cell D, and you want to prove that these two numbers are the same. So this means that you could roughly move one to the other via the action of PSLD, which preserves colors, and therefore these two numbers for C and D are going to be the same. Anyway, this is the claim that we need to prove. Do forgive me if I prove it and then finish. Okay. Anyway, here's the proof. So it is enough. You know what? I think I would give it to Alex anyway. I think I would stop here.